Hi everybody, this is lecture 2 about forces and Newton's first law, inertia. So inertia is kind of an interesting concept and a difficult one. And a lot of thinkers throughout history didn't really understand what inertia was. So it's okay if you don't understand it the first time through. So let's go through a little bit of history here. So Aristotle, this is a long time ago, was trying to figure out how objects moved. And according to Aristotle, there were two types of motion: natural, which is dependent on the nature of the object, and violent, resulting from pushing and pulling. And so he's really confused about what motion is and how it works in everyday life. If we skip ahead all the way to the 1500s, there's Galileo, who, instead of worrying about why they move, he was more worried about how they move. And he first one to show that experiment rather than logic is the best test of knowledge. So instead of trying to think everything through, let's go to the real world, test stuff out, drop stuff, push stuff, move stuff around, and see what happens. So this is sort of the beginning of the scientific method of experimentation over thought. And he was the first one to provide conclusive observation and experiment regarding falling bodies. So there's this famous experiment where he drops things off the Leaning Tower of Pisa, and he finds that the heavy and light objects hit the ground together. Okay, this is important. You wouldn't expect heavy and light objects to hit the ground at the same time. The complicating factor is the resistance from air. As the object rushes through air, sometimes the object is slowed down. But if we have similar objects, the light and heavy objects go to the ground at the same time. He also did some experiments with inclined planes. So if the slope is downward, speed increases. Slope upward, speed decreases. And so as the ball is rolling up the plane, the speed decreases. And if there's no slope, the speed does not change. It sounds kind of obvious, but it has a lot of implications about inertia. So let's read these over here. So the idea of inertia: if there is no interference with the moving object, it would keep moving in a straight line forever, with no push or pull necessary. So an object, if it's moving through space and there's no push or pull or forces or air resistance on it, it's just going to keep moving in a straight line forever. This is kind of weird because in everyday life, when we move things around, there's friction with a surface or friction with air that slows things down typically. So to put ourselves in a vacuum, to put ourselves in space, to put ourselves in an object's, what does an object feel? And to feel that it will move in a straight line forever unless something's acting on it, like friction or air resistance or a spring or a rope or a person. It's hard to imagine. So all of this discredited that old Aristotelian theory of motion. And then Isaac Newton comes along, a similar time frame, and he expanded on Galileo's ideas. He did all this by age 23 because he's Isaac Newton. And he claimed that the knowledge was a result of long thinking process, further supported by experimentation. So it was experimentation and thought together that gave him his ideas. And there's this anecdote of the apple falling on his head. I actually don't know if that's true, but the story is still there. So let's think of the law of inertia. Let's state it here. For Galileo said, a body moving on a level surface will continue in the same direction at a constant speed unless disturbed. Okay, and then Newton came along and refined this. Unless acted upon by a net unbalanced force, an object will maintain a constant velocity. So let's think about the Newton formulation of this. So we have the idea of a force, which we'll get into. So that's pushes and pulls and friction on an object. And if all of those forces add up to zero, that's the net unbalanced part, then the object will move in a straight line with no change in speed forever. Okay, so let's get into what this net unbalanced force thing is, so we can talk about what inertia is. Okay, so what's a force? The units of force, well, it's a Newton. Okay, the unit of force that we typically deal with in the United States is the pound. That's also a unit of force. But in physics, we're going to use the Newton. Sometimes it's a push, sometimes it's a pull. There's this support force, like right now I'm sitting on the ground. The ground is supporting me. That's the normal force. There's the gravitational force, which is the weight of the Earth pulling down on me. There's other kinds of forces. There's the external forces, internal forces. And a critical part is the force is a vector. So it's an arrow with a length and a direction. Okay, so we can think of it as an arrow. So let's get into this. So here is a, let's see, force of gravity and normal force. Here's a box resting on a surface. So the box is being pulled down by gravity. So we have an arrow down with some length, which represents the force of gravity. And then we have the normal force supporting the box from the surface. That also has a length and a direction, which is up in this case. We could have the box resting on a surface that's at an angle. The normal force supports the box, but now at an angle, so it's up and to the left. And gravity's still down, and that's straight down with a certain length. Now, in this case, the forces, the up force and the down force, will add to 0. So this box won't move. I think that's pretty intuitive. Over here, the normal force and the gravity force will not add to 0. And it'll slide down the surface, which I think is also intuitive. The reason this one doesn't move is the net force on the object is 0. And over here, it does move because the net force on the object is not 0. Okay, so let's state Newton's first law of motion. Every object continues in a state of rest or in a uniform speed in a straight line unless acted on by a non-zero net force. Okay, so that's what we're talking about here. The speed of this, the velocity of this box does not change because the net force is 0. The velocity of this one will change. It'll start to slide because the net force is not 0. Okay, let's talk more about net force. Also, net force is an addition of a bunch of forces. The units, again, is newtons. There are external forces acting on an object. So when we're adding up net forces, we always add up external forces on an object, not the internal forces holding the object together. And remember, the net force is also a vector. Okay, so let's look at this. We've got a gray box here with a 5 Newton force to the right and another 5 Newton force to the left. When we add those up, we get 10 newtons to the right. I think that's pretty intuitive. For the second example, we have 5 newtons to the left and 5 newtons to the right. Those are going to add up to 0 because now those forces are acting in the opposite direction. So this box will start to accelerate, will start to change its velocity because it's got a net force on it. This one will move at a constant velocity. Okay. Let's take a look. This is a check ourselves question here. What is the net force acting on the box? So let's look at this. We've got a couple answers here. We got 10 newtons to the right, 5 newtons to the left. So I think 5 newtons to the left is going to cancel out 5 newtons to the right. We'll be left overall with a 5 newtons to the right. So I think that's answer D. And that's right. Okay, the equilibrium rule. If an object maintains its motion, then the net force is 0. So before we said if the forces add up to 0, then we know the velocity is constant. But we can also flip it and say if we see something maintaining its motion, constant velocity, then we know the net force on that object is 0. This is called mechanical equilibrium. So if we have this plank right here supporting a couple workers, some paint in buckets, we've got gravity down on everybody, we've got some tension force from the strings holding things up. It's not moving. Therefore, the net force on that object must be 0. And that's what this says right here. So anything, if you look around your room right now, anything like the computer, it's sitting there not moving, we know net force is 0. I see a book over there, not moving, net force is 0. Anything not moving, we know net force is 0. Okay, this is the equilibrium rule. This is sigma F equals 0. So the sigma represents the sum of, and the force is the vector forces. So the sum of all the forces equals 0. That applies to vector quantities, scalar quantities, both or none. So since force is a vector, I think that's A. There we go. Okay, a bowling ball is in equilibrium when it is at rest. It's in equilibrium when it's at rest. Moves steadily in a straight line path. That's true. If it moves at a constant velocity in a straight line without moving, we know the sum of the forces is 0. We know it's in equilibrium, so I think this is both. Okay. All right, mass versus weight. So compared to that on Earth, what is an object's mass on another planet or in space? So mass is the amount of stuff that makes up an object. So if I have an object here, I got a coaster. The amount of mass in this object is always the same. Whether this is here on Earth or I put it in space, the mass is the same. I put it on the moon, the mass is the same. No matter where I put this object, mass is always the same. But if I put this on Earth, it has a certain weight because gravity is pulling it down. If I put this in space, it'll be weightless because there'll be no gravity acting on it. And if I put it on the moon, the weight will be 1/6 of the Earth's weight because the gravity on the moon is weaker. So the mass is how much stuff is in this object. It doesn't depend on where it is, but the weight depends on the gravitational field that the thing is in. So the mass is the amount of stuff that makes up an object. The amount of stuff does not change with location. Thus, the mass of an object is always constant, assuming you don't break it or something. How about an object's weight? The weight on another planet depends on the gravitational acceleration on that planet. So if we put it on the moon or Mars or Mercury, the weight will be totally different. And there'll be no weight in space. If you're in a weightless environment, there's no weight, even if things have mass. Okay, so we call weight is another name for the force of gravity on an object. And for us, here on Earth, the force of gravity, which we'll call F sub g, F subscript g, F sub g, equals the mass of the object times the gravitational acceleration of the object. And that for us is about 10 meters per second squared. Okay, and in free fall, this is motion under the influence of the force of gravity only. So if you throw a ball and you let go, it's going to start to fall in free fall until enough air resistance builds up on it. So if we drop 2 rocks of different masses at the same time from the same height, which one will hit the ground first and why? So if we drop 2 rocks, assuming we don't have air resistance, they're going to hit at the same time. But if we drop a rock and a feather at the same time from the same height, which one will hit the ground first? It'll be the rock, because the feather is going to get slowed down by air resistance. Okay, and here is rewriting the acceleration due to free fall. Before it was F equals mg, now we divide by m, we get F over m equals g. And for us here on Earth, it's about 10 meters per second per second. Okay, so non-free fall. So in free fall, the acceleration here on Earth is about 10 meters per second per second. But a lot of objects feel air resistance quite heavily. In fact, every object will feel it here on Earth because we have an atmosphere. So it's a really complicated force, air resistance. So making predictions about how objects will maneuver through an atmosphere is actually quite challenging. But we can say some things, like if we drop a feather, it's gonna fall much more slowly than a rock. We can say that. Okay, let's get a question here. When a 20 Newton falling object encounters a 5 newtons of air resistance, its acceleration of fall is, well, if it was in free fall, then the acceleration would be just g, or 10 meters per second per second. Since it's feeling air resistance, we know that that's going to slow down the acceleration. So that means we're going to be at less than free fall. So that would be A. I don't know what terminated means. I think that's, yeah, less than g. It's not going to be more than g because the friction will help to slow it down, not speed it up. Okay, let's do some more questions. According to Galileo, inertia is a force like any other force. That's not true. A special kind of force. That's not true. A property of all matter. That sounds right. A concept opposite to force. I'm not sure what that means, so I'm going to go with C. That's correct. A space probe in remote outer space continues moving because some kind of force acts on it. We know that's not true. Something moves in a straight line at a constant speed when nothing's acting on it. No, the net force is 0. It doesn't need force. In a curved path, it might move in a curved path if there's a force on it, but if there's no net force on it, it's just going to move in a straight line. C, even though no force acts on it. I think that sounds right. And due to gravity, that's not. It would free fall if it was in gravity. So a space probe far away from the sun is going to keep moving in a straight line, even though no force acts on it. Okay. When a 10-Newton object is suspended at rest by 2 vertical strands of rope, the tensions in the rope always... Okay, so a 10-Newton object is suspended at rest. So at rest means it's in equilibrium by 2 vertical strands of rope. The tensions in the rope always... Well, we know we have gravity down. That's 10 newtons. So the 2 ropes must cancel that out. So they must both add up to 10 newtons. Okay. When sign painters Burl and Paul stand on opposite ends of a scaffold, the tensions in the 2 supporting ropes, well, they may not be equal. We're not sure. Depend on the relative weights of Burl and Paul. That sounds good. Combine to equal 0? I don't think so, because we've got weights on Burl and Paul, and the tensions are both up. They're going to combine to something non-zero. And tensions in equilibrium, that doesn't make any sense, because the whole system should be in equilibrium or not. So I think it's the tensions in the supporting ropes depend on the relative weights of Burl and Paul. So I think that makes sense. If we go back to this picture of this scaffold, this one, the weights of these 2 people should change what the tensions in the rope are. It's going to depend on these weights. I think that makes intuitive sense. Okay, and let's see, let's keep going here. Okay, Burl and Paul have a total weight of 1,300 newtons. The tensions in the ropes that support the scaffold they stand on add to 1,700 newtons. The weight of the scaffold itself must be... Okay, so assuming they're in equilibrium, and Burl and Paul's weights are 1,300 newtons down, and the tension in the ropes are 1,700 newtons up, that means there's a difference of 400 newtons, so the scaffold itself must weigh 400 newtons. Okay. The Earth moves about 30 kilometers per second relative to the sun. When you jump upward in front of a wall, the wall doesn't slam into you at 30 kilometers per second. Okay, that's true. This is because the wall has too little gravity to influence you. I'm not sure what that means. Moves in an opposite direction to you. That's not true. It's moving with you. You are moving at the same horizontal speed before, during, and after the jump. I think that sounds right. Has negligible inertia compared to the sun. So this is because the wall and you are moving at the same horizontal speed before, during, and after the jump. So this is a statement about inertia. The wall is moving at a certain speed. You are moving at a certain speed. There's no external net force on you to slow anybody down. So we're both, you and the wall will move together at a constant velocity for that moment you're jumping. That's inertia. That's why we don't slam into walls when we're going around the sun. So that's D, that's C. Okay, and that's it. If you have any questions about inertia or Newton's law, first law, let me know. Please email me. And I'll see you guys for lecture 3 next week.